You know, every single app on your phone, every website you browse, none of it just magically appeared. It was built. But how do you go from just a cool idea to a huge, complex system that actually works without everything falling into total chaos? Well, the answer is something called a software process. And in this explainer, we're going to pull back the curtain and show you the structured methods that bring order to the madness of creating software. So here's what we're going to cover. We'll kick things off with what a software process even is, then we'll break down the 4 core activities that are in literally every single project. After that, we'll check out 3 classic models, see how they deal with the one thing you can't avoid, change, and look at a modern hybrid example before we wrap it all up with the key takeaways you really need to know. All right, let's jump right in. First things first, what exactly is a software process? Well, think of it as the master blueprint for building any piece of software. And trust me, you absolutely need a blueprint when you start talking about the big stuff. I mean, how do thousands of engineers all work together to build something like a new operating system or a global banking app? They don't just, start writing code and hope for the best. They have to have a plan. And that plan, that's the software process. It's really just a structured set of activities that takes a project from a vague idea all the way to a finished product. It's the framework that keeps everyone on the same page, building the same thing, so you end up with a system that's reliable and actually does what it's supposed to do. But here's the really interesting part. No matter how different these processes might seem on the surface, you've got some that are super rigid and others that are incredibly flexible, they all share the same fundamental DNA. They're all built from the same 4 core activities. First up, you have specification. This is all about figuring out and defining what the system is supposed to do. Then you've got design and implementation. That's where you map everything out and, well, write the code. After that comes validation, which is just a fancy way of saying you test the heck out of it to make sure it's what the customer actually wanted. And finally, there's evolution, because software is never really done, right? It always has to change and adapt over its lifetime. So, if every process is made from those same 4 ingredients, what makes them so different? It all comes down to the recipe, the model for how you organize those activities. Let's take a look at 3 of the classic approaches. Now, before we get into the models themselves, you gotta understand that there are 2 main philosophies, 2 big camps. On one side, you've got plan-driven processes, where you try to map out every single detail in advance. On the other side, you have agile processes, where the plan evolves as you go. Keep those 2 ideas in your head, because the best modern processes usually find a way to blend them. So, first up is the original, the granddaddy of them all, the waterfall model. This is as plan-driven as it gets. Literally, think of a real waterfall. Once the water flows over one level, it can't go back up. It's the same here. You have to finish all your requirements gathering before you can start designing. Then you have to finish all your design before you can write a single line of code. It's a very strict one-way street. And you can probably guess its biggest weakness right away. It is incredibly inflexible. What if your customer changes their mind halfway through? It's a total nightmare because going backwards is super expensive and difficult. That's why waterfall really only works for projects where you know exactly what you need from day one and that it will never change. Like, say, software for a satellite, not a brand new social media app. So how do you solve that rigidity problem? Well, you build things incrementally. Instead of one massive delivery at the very end of the project, you build and release the software in small, working chunks. And this is a total game changer because you get feedback from real users on working software right away. That makes it way cheaper to adapt to changes, and your customers get something useful in their hands much, much sooner. But, of course, this way has its own problems. All that constant change can make it tough for managers to see the big picture. And if you're not careful, the code itself can start to degrade. It's like constantly renovating a house without ever checking the foundation. If you don't take dedicated time to clean things up, what we call refactoring, the system can become a tangled mess that's hard to work with down the road. Our third model is all about a simple idea. Don't reinvent the wheel. With reuse-oriented engineering, the whole point is to build your system by plugging together parts that already exist. This could be using commercial off-the-shelf software or COTS, like using Google's mapping service or Stripe's payment system, instead of trying to build your own from scratch. It's all about speed and efficiency. So by now, you've probably spotted the big theme running through all of this. All these different models, they're really just different strategies for dealing with the one thing that is guaranteed in software: change. And you can boil down the strategies into two main approaches. The first is change avoidance, where you try to predict and get ahead of changes before they cause big, expensive problems. The other is change tolerance, where you just accept that change is going to happen and you design your process to handle it cheaply and easily. Incremental development is a perfect example of change tolerance. Prototyping is a classic example of change avoidance. It's kind of like an architect building a little cardboard model before they build the actual skyscraper. You quickly build a cheap, throwaway version of your software to let users actually click around and play with it. That way, you find out they hate your design before you've spent 6 months building it for real. Okay, so we've got these different models, these different strategies. How does this all fit together in the real world today? Well, the answer is usually some kind of hybrid. Let's look at a famous example that tried to create a best of both worlds framework. This here is a look at the Rational Unified Process, or RUP. Now, the big idea with RUP is to separate the what from the when. See these activities on the left, like requirements and testing? In RUP, those things are happening all the time, in parallel throughout the project. This lets the process feel structured while still being super iterative, so you're moving in cycles instead of a single straight line. So you can see what RUP is trying to do here. It's grabbing the best ideas from all over the place, like the structure you get from careful planning, but also the flexibility you get from building iteratively. It's basically a big, formal attempt to find that sweet spot right between total chaos and being so rigid you can't breathe. Whew, okay, we have covered a ton of ground here, from the basic DNA of a process to some pretty specific models. So let's bring it all home and boil this down to the key things you should remember. So what are the big takeaways? Number one, every single process, I don't care which one, is just a mix of those 4 activities: specification, design, validation, and evolution. Number two, models like WATERFALL and INCREMENTAL are just different recipes for mixing them together. And this is the most important one. There is no best process. The right one always depends on the project. And finally, the most effective approaches today blend the foresight of a good plan with the agility to adapt when things change. And that leaves us with one final big question to chew on. For decades, all of these processes were designed for humans to follow. But now, as AI starts to write code, test code, and even design software, what happens to these blueprints? What does a software process even look like when the person or thing building the software is part machine? Now that is something to think about.